Alright, this video is to help us understand how to compute what are called compound probabilities, and typically using what we're going to use is the addition rule. Basically, a basic probability, again, remember, is just to calculate the probability of what you want to have happen divided by the probability of everything that could happen, or the amount of ways that everything could happen. So the probability of drawing a club, if you're drawing one card from a standard poker deck of cards, a 52 card deck, is, well, there are 13 clubs, and so any one of those will be fine for us, divided by the total number of 52 cards. So again, what we want to have happen, those 13 cards, versus what could happen, the 52 cards. If we reduce that to 1/4, or find its decimal, 0.25, then we have its probability. Well, the probability of a heart, a diamond, or a spade, if we draw one card, the probability that one card is either a heart, a diamond, or a spade, well, we just basically need to say there are 13 hearts, there are 13 diamonds, and there are 13 spades, and we're okay with any one of those. So one way to calculate that is just to take all of those cards, again, and add them up. And that's the basic idea of, if we see that word or, then essentially we're going to kind of think about that addition rule, adding them together. So if we do that, 13 plus 13 plus 13, essentially we get 39 out of 52, or 3/4. And that becomes a 0.75 probability of happening. Now, you may have also wanted to think about, well, we could use what's called the complement. We'll talk about that more later on. But we could have also said, well, hey, if we want a heart, a diamond, or a spade, then the only thing we don't want is a club. So we could have taken 100% of everything happening, or a probability of 1, to guarantee that something happens, and subtract off the only things we don't want to have happen. Well, we know the probability of a club was 0.25. And so it makes sense that the probability of anything else happening would be 0.75. So again, that's also a way we can get to that probability. A face card or an ace. Well, the probability of drawing one card and having it being a face card or an ace, this next chance, well, again, the same idea. Let's think about, well, we can't do a complement this time because we don't really know non-face card or ace. We haven't really calculated that. So let's just go straight for our answer. We know there are 12 face cards. We know there are 4 aces. So again, I would add all of those cards up, essentially saying there are 16 out of 52 cards that we would be okay with, and 16 over 52 is a 0.308 probability. So fairly simple there. Let's consider one more scenario, the probability that it's either a jack or a diamond. Well, there are 4 jacks in the deck, and there are 13 diamonds in the deck. A diamond is, again, a suit, so much like a club, there are going to be 13 cards in the deck. Well, 4 cards plus 13 cards, you would think would be 17 cards out of the 52 cards. However, you have to be careful when it comes to jacks and diamonds, because in these previous examples, we had what were called mutually exclusive examples. Mutually exclusive or disjoint examples are probabilities that can't happen at the same time. We can't draw one card and have it be both a face card and an ace. They're not the same thing. Or the same idea, we can't draw a heart that's also either a diamond or a spade. We can't draw one card that would satisfy more than one category. However, when we think about jacks and diamonds, there is one card in the deck that is both a jack and a diamond. So when we think about those compound events, we have to also think of that intersection. And for a general compound event, not one that's necessarily mutually exclusive, what we can do is add the probability of the first event, so the probability of a jack, to the probability of the second event, the probability of the diamond, but then we need to subtract off any intersection, because technically the jack of diamonds is one of the 4 jacks, it's also one of the 13 diamonds, and we've double counted that if we count 17 cards. So we need to take it away one of those 2 times, essentially telling us there are 13 jacks and diamonds, not double counting that jack of diamonds, in the deck. That general rule is a very helpful thing for us when we talk about the union of 2 events, or basically talking about that word or. If something can be either the probability of A or it could be in B, but there's an intersection, it can technically be both, then we got to make sure we don't double count those cards or double count those probabilities. So the general rule is, again, the probability of A or B, again, the union, this U symbol, is equal to the probability of A plus the probability of B minus the probability of A and B, that intersection, that upside down U. The probability of the intersection, or double counting that middle. Again, if they are mutually exclusive events, that's like a Venn diagram that doesn't cross over. So now when I add up A and I add up B, it's not a problem. So just keep in mind, again, if the intersection is 0, you're subtracting off 0. Basically, your mutually exclusive events are happening, and you can just add the two probabilities. And then finally, we also talked a little bit about the complement. The complement of an event is the probability that an event won't happen. Or basically, an easy way to find that is 1 minus the probability of event A happening. That would be equal to the complement. And a couple ways to represent that are P of not A. Again, your probability of something not happening. If you ever see a bar in the lower left here, a bar over the A, that means the probability of it not happening. And another way to represent that would be the probability of this little tilde A. Essentially means the same thing. If you ever see that, again, it means not A. Probability of that thing not happening. All right. Let's look at a couple more examples. If we talk just straight math, a great idea is, again, when you're using that general rule, you just have to be careful what information you know. If I know the probability of A happening and the probability of B happening individually, but I also know the probability of their intersection, 0.31, well, the one thing I can do is set up that the probability of A plus B minus the intersection, again, would be the probability of A or B. So I can kind of put those pieces together and fill in what I know, and very quickly and easily, again, add the two probabilities, but subtract their intersection, and we can find the probability of A or B happening. Again, not just happening together, but either A or B, or both, for that matter. The probability of A or B not happening, again, if this is the complement, therefore would be 1 minus 0.52, or 0.48. All right, now let's consider, what if we have other information? What if we have the probability that A happens and the probability that B happens, but we also already know the probability that A or B happens? Again, you just need to fill in your information into the correct parts. We know the probability of A and B. We know the probability of A or B. What we don't know is the probability of A and B. So we can kind of fill in the pieces. Again, we can add the like terms. We can even kind of switch spots here. If the probability of A and B is negative currently, I'm going to go ahead and add that to the other side, and at the same time subtract that 0.7 over to the right side. That way we can get the probability of A and B all by itself, and 0.8 minus 0.7 would be 0.1. And if we wanted to find the complement of that idea, again, just a real quick switch, all we have to do is take 1 minus 0.1, and there'd be a 90% chance of A and B not happening. Again, it's just a great way to use that formula. It's just a formula, easy way to kind of set up that probability of A or B being the probability of A and B subtracted from the probability of A or B happening individually. All right, in the real world, here's just a couple of quick situations where you might see this kind of thing. If you buy a pair of pants in your regular size without trying them on, there's a 30% chance, basically, that they're too tight, 10% chance they'll be too loose. If they're too tight or too loose, then they don't fit. So if we just randomly select that pair of pants at the store, we think they're going to be good, we go home, don't try them on at the store, right? We're someplace we can't do that. We bring them home. What's the probability that the pants do not fit? Well, to be too tight or too loose essentially are two ends of the spectrum. So we would assume mutually exclusive events, two events that can't happen at the same time. Pants are either going to be too tight or they're going to be too loose. Okay? So we can just add those two events together. They're mutually exclusive again. Two things that won't have an intersection. So 0.3 plus 0.1. There's a 40% chance, or 0.4 probability, that those two events, right, a probability that the pants do not fit. Well, if that's the case, what's the probability that the pants do fit? Well, if we know that it's already 0.4, we don't have to use a lot of time rethinking our problem. If there's a 40% chance that they don't fit, then the probability that they do fit is just 1 minus that, or the complement of that event. So there's a 60% chance then that they will fit. If we use an educated guess, basically if we just bring them home and try them on, there's a 60% chance we're going to be pretty good. Well, how about the one at the bottom? Records show that the number of students preparing for their high school equivalency test, 80% need help in math, 70% need help in English, and 55% need help in both areas. Well, that means that we do have an intersection. So this isn't a mutually exclusive event. This is more of a general idea. The probability of needing help in math plus the probability of being helped in English minus the probability of needing that help in both subjects, right? Needing that help both ways would be equal to the probability of math or English or both. Okay? But we need to subtract that intersection because, again, 55% of both areas, essentially, that 0.55, falls into both categories. And we can't double count, right? If all we did was add them up, well, we would be saying that 150% of people need help in math or English. And that just wouldn't make any sense because we have that huge crossover in the middle. Okay? So what we can do is fill in our information, though. 0.8 plus 0.7 minus 0.55. And we would find out that there's a 95% chance that someone might need help in math or English or both. But now we got to read carefully, though. I didn't read through that last part of the question. Find the probability that a student does not, right, doesn't need any help with either math or English. Well, if this is the probability that they need help with either math or English or both, the probability that they don't need any help at all would, again, just be that complement. 1 minus 95%, there's a 5% chance, right? Or if both circles added together were 95%, there's a 5% of the population that wouldn't need help either way. Again, I hope that helps you with compound probabilities and the addition rule. If you have any further questions, make sure you talk to your teacher. Good luck and have a great day. Happy counting.